Hey everyone, and welcome to this explainer. Today, we are tackling an absolute classic, one of the most famous coding challenges out there, the maximum subarray sum problem. Now, we're not just going to throw a massive block of code on the screen and read it to you. Nope, we're actually going to trace the visual evolution of the solution. We'll start with just raw human intuition, translate that into a super clever algorithm, and then break it all down using advanced computer science theory so you can see exactly why it ticks. So if you've ever felt stuck trying to bridge that gap between a clunky brute force idea and a beautiful, optimized solution, well, you're in the exact right place. Let's get right into it. All right, here's our quick roadmap for today. We'll start with Section 1, the core problem. Then Section 2, intuition and linear tracking. Section 3 is the crossroads. Section 4 covers Kadane's algorithm. Section 5 dives into the dynamic programming approach. And finally, Section 6, the optimized solution. Okay, let's dive into Section 1, the core problem. Let's figure out exactly what we're up against here. So, we are handed an input array of integers, right? And our mission is to find the contiguous subarray that gives us the largest possible sum. Now listen, if this array was just packed with positive numbers, this wouldn't even be a puzzle. You'd literally just add them all up and call it a day. But we've got negative numbers thrown into the mix. And honestly, they're the real villains of this story. Now, your first instinct might be brute force. Just check every single possible subarray combination. But doing that means you're writing a nested loop, which sends your time complexity straight through the roof to a very sluggish O of n squared. We need something faster. We really need a way to scan this array just one single time. To find that faster method, let's roll into Section 2, intuition and linear tracking. We're going to mentally walk through this array step by step, kind of simulating it as if we were the algorithm itself. We start right at index 0. To hunt down that maximum sum, let's try keeping a running tally of our contiguous subarray. We'll initialize our current sum, let's just call it cur_sum, with our very first value, which is a 3. Okay, so far so good. Our running sum is a solid positive 3. Now let's move over to index 1 and see how this builds as we stretch our subarray to the right. We step onto index 1, and hey, it holds the value 1. Since it's positive, we gladly add it to our running total. Our cur_sum seamlessly ticks up from 3 to 4. Everything is working like a charm. But then, disaster strikes. We expand over to index 2, and bam, we hit a massive pothole, a -6. We add this to our hard-earned sum of 4, and suddenly our cur_sum completely tanks into the negatives. It drops all the way down to -2. So literally all the progress we made from those first two numbers totally wiped out by one single negative integer. And hitting a negative number like that, it forces our algorithm into a massive decision point, which brings us to Section 3, the crossroads. I want you to really think about this for a second. What should we do right now? We're just standing there holding a totally depressing running sum of -2. The next number in the array is just waiting for us. So do we force that next number to join our failing negative subarray, or do we just cut our losses and start completely fresh? Let's actually look at the math to prove which choice is better. The next number up at index 3 is a positive 2. Now, if we go with choice 1 and stubbornly continue our current subarray, we add that positive 2 to our -2 baggage, bringing our brand new sum to exactly 0. Yikes! But look at choice 2. If we decide to just restart a brand new subarray right here at index 3, our new starting sum is literally just the value of the number itself, which is 2. And since 2 is obviously greater than 0, it is undeniably better to just drop the deadweight from the past and start fresh. And that realization brings us to Section 4, Kadane's algorithm. Because that completely intuitive decision we just made, it actually forms the foundation of a legendary piece of computer science theory. Welcome to Kadane's algorithm. Look at this incredibly elegant formula. At every single step through the array, the algorithm is calculating two things: your current sum plus the new number, compared against just the new number all by itself, and then it simply takes the maximum of those two values. So the absolute genius of this is that the formula is constantly asking itself, hey, am I better off dragging the past along with me, or am I better off just starting over right now? Let's actually see this in action. We're at index 4, which is a -1. Our cur_sum coming into this step is 2. Let's run the formula. We calculate the max of 2 plus -1 versus just -1. The maximum between 1 and -1 is, well, 1, And this brilliantly highlights why Kadane's algorithm is just so powerful. It realizes that, sure, the -1 drops our score a little bit, but our historical sum of 2 is strong enough to absorb the blow. It keeps our total in the positive, so we don't restart. We swallow the negative and keep the chain going. And taking that little hit, it pays off immediately. At index 5, we hit a +4. Because we kept our chain alive, we add that 4 to our running sum of 1, hitting a massive peak sum of 5. Now there's a really crucial detail you gotta notice here. As we traverse this array, our cur sum is bouncing up and down. So to solve the actual problem, we absolutely have to maintain a completely separate variable, we'll call it max sum, just to record the highest peak we ever hit along the way. In this specific case, 5 is the absolute highest sum we'll ever encounter, which effectively gives us the final answer. Now, because Kadane's algorithm literally just sweeps through the array one single time making these quick local decisions, the time complexity is beautifully linear. It runs at O of n. And even better, because we only need to keep track of a couple of tiny integer variables, just the current sum and the max sum, our space complexity is O of 1. It is ridiculously efficient. But hey, we're not stopping there. To truly master this, let's move into section 5, dynamic programming approach. We are actually going to reverse engineer Kadane's algorithm. So the whole philosophy behind dynamic programming, or DP, is taking a massive, overwhelming problem and breaking it down into smaller, overlapping subproblems. A really key observation here is that every possible subarray has to end at a specific index. That means we can actually define our subproblems like this. Hey, what is the maximum subarray sum that strictly ends at index 3? Or what's the maximum subarray sum that strictly ends at index 4? Every single index represents its own little distinct universe of possibilities. Now, what's genuinely fascinating is how these subproblems hook together. Let's pick a random index. Let's call it I. The maximum subarray ending at I absolutely has to include the number at index I, but what else is in there? Well, it just looks backward. It depends entirely on the maximum subarray that ended right before it, at index I-1. If the subproblem right before it gave us a positive boost, we happily attach our current number to it. But if the subproblem before it was a net negative, we just cut it off and start a brand new subarray with our current number. If that logic is sounding a little familiar to you, it's because it's the exact same intuition we used earlier. But right here, it's formalized as a proper dynamic programming recurrence relation. Our DP array at index I equals the maximum between the previous DP value plus our current number, or just the current number all by itself. The base case is super simple. The first element in our DP array is just the first number in the input array, and from there we systematically build out the rest of the array, solving every subproblem step by step. But there's a catch. If we look at the complexity table for this traditional DP approach, we spot a clear trade-off. While our time complexity stays at a really speedy O of n, our space complexity has totally ballooned up to O of n. Why? Because to do textbook dynamic programming, we had to spin up an entirely new array just to store the answers to every single subproblem along the way. And that perfectly sets up our final section, section 6, the optimized solution. This is where we bring these two worlds together and find the ultimate perfect solution. Think back to our DP formula for a second. To calculate the value at the current index, how far back did we actually have to look? Just one single step. We only ever needed the value at dp of I-1. We never cared about the values from 2 steps back or 3 steps back. So why on earth are we wasting precious memory storing the entire history of these subproblems in some giant array? We don't need to. We can optimize this by trashing the array completely and just using a single tracking variable that updates itself at every step. And boom, by doing that, our space complexity drops right back down to O of 1. And here is the massive aha moment. When you optimize the space complexity of the dynamic programming approach, you end up with the exact same code as Kadane's algorithm. This brilliantly proves how sometimes solving a problem through raw, logical, human intuition leads you directly to a highly optimized dynamic programming solution without you even realizing it. They are literally two sides of the exact same mathematical coin. We've just seen how recognizing a simple optimal substructure, realizing that today's best choice relies only on yesterday's best outcome, transformed a sluggish, nested loop nightmare into an elegant linear breeze. So I'm going to leave you with this question. What other inefficient, messy logic in your own code might secretly be hiding a beautiful, dynamic programming solution just waiting to be uncovered? Thank you so much for joining me for this explainer. Keep optimizing your code, and I'll catch you next time.